Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hi everyone, and welcome to a new webinar in our quantum computing workshop series. These workshops will lead up to the Future Leaders in Quantum Hackathon, or QC for short, which will happen in mid-May. This hackathon is co-organized by the International Telecommunication Union and the Quantum Coalition, a global student-led network of quantum computing clubs. You can register for QC Fleek and check out recordings of past workshops on the AI for Good website. Be sure to stay tuned for more updates and upcoming quantum computing lectures. Today's workshop dives into high-level quantum software design with hands-on examples. I'm excited to introduce today's speaker, Nadav Ben-Ami, a quantum algorithms engineer and community manager at Classiq, which is a leading quantum software company that empowers users to design, synthesize, and optimize quantum circuits at scale. Their platform abstracts low-level gate implementation, allowing developers to focus on algorithmic innovation and performance. Nadav, the floor is yours.
Thank you, Dimitri. So, hello everyone. Welcome to the hands-on lab on designing quantum algorithms with Classiq. My name is Nadav Ben-Ami, and I hope you're going to enjoy and get some value from this workshop. So, a little bit about myself. My name is Nadav Ben-Ami. I'm quantum algorithms engineer and community manager at Classiq. As Dimitri said, I joined Classiq after the MIT Hackathon 2024, where my team secured the first place in the hackathon. Before that, I was visiting summer research at the Munich Center for Quantum Science and Technology. And my background is actually from physics and optics in Tel Aviv University, where I was research intern, and later on also in KLA, where I was doing imaging for semiconductor industry. So enough about myself, and our agenda for today is as follows. We're going to discuss a quantum software paradigm shift, why we need to change the current software paradigm from low level to high level, what are the challenges, and what Classiq offer to solve those challenges. Afterwards, we're going to move to a live demo, where you're gonna see in firsthand what is the change of paradigm that Classiq offers and what our platform includes. And later on, I would include some further information and material for you to get hands-on practice and how you can stay connected with me and my team. So first thing first, let's dive into the change of quantum software paradigm. So before, just to give some context, what is the key challenge of current quantum software and algorithms design? So we have on the one hand domain-specific problems, and on the other hand, the quantum algorithms. In domain-specific problems, we refer to the most difficult problems that we currently cannot solve with the classical and quantum computational tools. We have problems in condensed matter physics, in quantum chemistry, in finance, in logistics, and many more. And on the other hand, we have quantum algorithms like QSVT, HHL, quantum phase estimation, Shor algorithm, Grover, and many more. And the problem is, of course, first identifying the problems which we cannot solve and trying to find an algorithms that suit for them. So basically, we want to expand each of these categories and eventually link between them. Summarizing this up, the main goal is to develop both efficient and useful quantum algorithms to solve the most challenging problems of humanity, to benefit and to move to the next stage. To get some idea of how we're gonna do that, we're gonna discuss first about classical algorithms to get some inspiration, understand the shift in technology in past revolutions, and maybe to take inspiration for the future of quantum software. Here we have an example of high-level language, which we all know, Python. So we have here a mathematical expression, basically implementation of a very simple algorithm, which is 2x to the power of 2 minus 5x plus 3 for a discrete range. This is very simple algorithm in single line, very clear to understand what it does. And that's the power of high-level language. On the other hand, we have a low-level language. We have assembly example that do exactly the same algorithm. It runs exactly the same algorithm, but not in a single line of code, but rather in 40 lines of code. The reason for that is that we need to take care of many details that we don't care about in Python and in high level, like initializing the loop, checking in each step that the loop is still within the range of iterations, allocating memory to specific registers, and so on. All of these details are not interesting for someone who's trying to express mathematical concept of this equation. In exactly the same manner, in quantum algorithms development, we have a similar situation today. Here we have implementation of a specific algorithm, which is not so clear from this visualization representation what this algorithm is actually doing. We have the power block, which is higher level, but the rest is just Hadamard gates, T gates, control X, and so on. And it's not clear what it does. That's a low-level way of thinking. It's heavy, it's complex, and not always so clear. And it's have to done manually to allocate each gate on each qubit. On the other hand, we have the same algorithm implemented with the QMod language, the high-level quantum software language we develop in Classiq. And that makes things a little bit more clear. So we have a QFunc, meaning quantum function. We have a main function, which called main. It's always, we have a main in the QMod language, which kind of aggregate the entire model into one quantum model. We have two outputs, X and Y, which are both QNum, quantum numbers. We allocate X with 4 qubits. This is what you can see here. And then we go through Hadamard transform. So yeah, this is exactly what you can see here, the 4 qubits through Hadamard transform. The rest of the algorithm is done with a single line of code, y equal x to the square plus 1. So basically, we put x in a coherent state, in an equal superposition, and we perform this calculation in parallel on all possibilities of the register x. So I think that's already demonstrates a value of the high-level language, because we don't specify here gates except of these 4 Hadamard gates, right? The rest is done automatically by our synthesis engine, which we will talk about later. And that's not the only advantage of moving to a higher level of way of thinking. Another advantage is that, as probably most of you know, there is many different hardware modalities for quantum computing. Neutral atoms, ion traps, superconducting qubits, and so on. And each one of them have different properties, different limitations, different connectivity maps between the qubits. And because of that, also different way of best optimized implementation for the algorithm. When we design this algorithm in low level, we basically already choosing the concrete implementation. So we basically connect together the algorithmic concept and the actual implementation, just as we saw in assembly in the classical domain. On the quantum domain, though, if we go to the higher level of abstraction, we can quick, easily different implementation to different basis gates, different number of qubits, and so on. So you can see here we have, again, the 4 qubits in Hadamard under the Hadamard transformation, but the rest of the implementation is different. So here we had 21 qubits, and here we also only have 11. And we use different gates to create the same algorithm on different under different constraint or different hardware. So I think this is already demonstrating the power of moving to high-level way of thinking. Another challenge and another reason to scale and to move from the low-level to the high-level way of thinking is presented here. So basically, if we do textbook implementation with 4 or 5 qubits, with single amount of qubits, that's quite easy. We can use the tools we all know, like Qiskit. It's great. You can use controlled and allocating each gate on each qubit and measuring post-processing, and it's quite doable. But if you go to tens of qubits, that get more and more complex, and understanding what this algorithm is doing is already a little bit difficult. And if we go even further, when we have thousands of gates and hundreds of qubits, that will be impossible to understand what the algorithm is doing. It will be impossible to follow the flow of the information and to actually understand what the algorithm is doing. So put that in mind, because we're gonna see how this challenge was solved later on by Classiq, and this is very much related to the need in the shift paradigm. Because of this, those challenges in Classiq, we go in the direction of functional building blocks. And this play 2 roles. So on the first hand, it's helped to reduce the complexity and kind of communicating with the quantum computer in a higher level way of thinking in different language, which is more easy to understand and to scale. But also on the other hand, in the theoretical level, the quantum community is trying to develop more and more quantum toolbox, basically tools like amplitude amplification or quantum phase estimation. And all of these building blocks later on used to aggregate into larger algorithms to solve larger sets of problems. So this is very much resonate with the idea of what we're trying to do and to abstract the concept from quantum mechanics and quantum computing into a quantum domain-specific language. The inspiration for this concept comes from classical circuit design of electronical circuits. So I guess some of you know the VHDL language, the Verilog, all the hardware languages, which basically at the beginning when we could route a transistor by transistor and gate by gate, that was great. But with the scale of classical processing units, we got into million and trillion of transistor on a chip. And that's demand change in the paradigm and the way of thinking. And over here, we don't really allocate transistor by transistor. I'm not an expert to hardware languages, but the idea here that they abstract a concept of hardware to create an electronic circuit. So we communicate with the computer in a language and in a logic that much more fits to the way we think or in the way of scale. And we get later on by automation and actual implementation. In the exact same way, we're trying to do in a Classiq. So we have the QMod, as I already mentioned, the quantum modeling language. It's a domain-specific language. And here we have a simple implementation of the Bernstein-Vazirani algorithm in the native syntax of QMod. We also have Python interface, but we will get to that later. So we have here 3 quantum functions. The first one is Bernstein-Vazirani predict, BV predict. We have a repeat, which is a kind of a for loop. We have if statement with some arithmetic condition. And if it's complied, we apply some CX gate. Otherwise, we do nothing. We apply the identity. This function is later called here. BV predict is called within the Bernstein-Vazirani function. where we use the Hadamard transform. We use the within apply concept, which is the UVU dagger from quantum mechanics, a very well-known and commonly used subroutine. And yeah, then we apply the BV predict and the Hadamard transform again. We call these two functions in the main. We allocate 5 qubits to X and call the BV function, which calling later on to the BV predict, and we get an actual implementation. We don't need to specify all the details of this arithmetic expression. This is done automatically. And by tweaking the constraints, we can get different implementation to the same algorithm. Trying to...
Sorry, Nadav.
Yes, Dimitri.
How does Classiq handle hardware-specific constraints when optimizing circuits?
Well, this is basically our secret sauce, though, but the general idea is every quantum computer have different basis gates. Some use a specific gate, some use others, some have this connectivity map, and some have all-to-all connectivity map. In the end, it's many constraints, and it's a computationally difficult problem to solve, to choose which implementation to actually choose from all the possibilities. Later on, we will see that more in firsthand, but I think it was here. So as you can see here, there is various of implementation for adder or for multiplier. Choosing the right implementation also very much depends on the basis gates and the specific constraint for each hardware. So that's a very difficult problem to solve computationally. And at Classiq, we try to do that. I hope it's answered the question.
Thank you.
Is there any other questions? All right. I take that as no. So what is Classiq? It's basically end-to-end quantum software solution. We have our platform and we have our flow, which go through modeling. We have the QMod native language. We have also the Python interface. We will see that later, which kind of combine the power of the domain-specific language with Python and many of its libraries like PyTorch for quantum machine learning application and so on. We have the synthesis engine that does exactly what I was just explaining for the question from Dimitri, that solve the problem, a difficult problem, that find the most optimal implementation of the circuit. We have very cool interactive visualizer for debugging and actually visualizing large-scale quantum circuits. And in the end, we have execution integration with many hardware providers from AWS Braket, Azure Quantum, IBM, Google, Alice and Bob, IonQ, and many more. We keep expanding this list to support as many universal gate-based quantum computers, and also many hardware high-performance computing centers. So summarizing in a single sentence, we try to take the how to implement a quantum circuit from the designers and just letting them focus on what they want to do, to letting them express the algorithmic concepts in high level. Now we will move to the live demo. So you can actually see the platform and experience it. So this is the landing page of the platform. You can go to platform.classiq.io. You need an academic email to register, and if not, you can email us and get access in the personal cases. You can have a walkthrough here, but we skip that for this session. You can join our Slack community. You can get a quick link to our documentation 101 and quick links to different implementations. And here you have the flow where we're going to focus. So we have the model, the quantum program, the execution, and the executed jobs management. Later on, we will see also the Classiq Studio. We also have graphical modeling, but we leave it for later and focus on the QMod native and the Python SDK. So here you have the IDE for the QMod native language. You can click here and get access to our library of algorithms and choose whatever algorithm you wish for. We have implementations of many algorithms and applications. You can play with it. But for the sake of the example, we choose arithmetic expression, the larger arithmetic example here. So what we have here, we have a qfunc again, a main function with output z, which is a qnum, a quantum number. We have x and y quantum numbers as well, declared as local variables, and we give them the values 2 and 1, which are automatically encoded to the quantum circuit later on. And what this function is doing, it's ask whether z is the value of z with this arithmetic expression is larger or smaller than 4. Basically, we want to know it's a Boolean variable that check whether this expression is larger than 4 or not. So we have here 2x, which means 4 plus y, it's 1. So it's 5, it's already greater than 4. And we also take the max between 3 to 2. So we have 8, which 8 is definitely larger than 4. Here you can set different constraints like maximal width, maximal depth, optimize to width, depth, no optimization at all, or different transpile basis gates. Here you have more advanced preferences like choosing backends to optimize for specific hardware, basis of gates and connectivity maps, customized and so on. For this example, let's do just depth with no optimization and with no other constraints. So now all we have to do is to press synthesize and wait for a few seconds, and we're going to get an actual concrete implementation of this logic. So we are directed to the quantum program page, and this is our visualization tool. So we have here x variable on 2 qubits and y variable on 1 qubit. We can go to see in a lower level the concept, or the actual implementation. We can stay in high level, and we can check this logic here. This is our arithmetic expression. We have 32 qubits with depths of 216. This is the transpiled program, so the actual implementation that's going to run on the simulator. And if we want to see the logic within here, this is nothing that we did by hands, right? This is all automatically produced for us. We can see the implementation of the multiplier. We can see the implementation of the adder. We can go deeper. We can go backward and back to the high-level way of viewing the algorithm. So we basically can see the flow of the algorithm both on high level and low level in the same time. And now let's go for execute, and we're going to have a problem because 32 qubits and our simulator is limited to 25 qubits. So what we're going to do, let's go back to our modeling page, and let's limit ourselves to 11 qubits. Now we can resynthesis and create a new quantum circuit, a new implementation. Again, we can wait, we should wait for a few seconds. All right, we got a new implementation. This time we reduced the count of qubits to 11 from 32. That's quite significant. And we paired with about 30 more depth in gates, which is manageable. And let's see how the multiplier looks now. Quite similar, maybe the adder change. Yes, the adder, if you remember, the other one was with CX gates. Here we have QFTs and control phased. So basically we got a different implementation. And we have all the greater than all the details here. We can dive deeper or go backward, to the high-level way of viewing the algorithm. Now, when we have only 11 qubits, we can actually execute on our Classiq simulator. By the way, that's a great point to show all the backend providers. So we have our own simulators, we have NVIDIA simulators, bracket simulators, we have IBM machines, we have access to Azure Quantum with IonQ, Rigetti, Quantinuum, also through Amazon Bracket and IonQ directly, and Google, and Alice and Bob, and Intel, and many more to come. So that's basically very convenient. You don't need to rewrite your code or to adapt it to different platforms. You can do it all from one unified platform. And for now, we're going to run it on our simulator. That's not the result. Let's wait for a moment. And we got Z equal 1, mean true, because 8 is actually greater than 4. This is not a surprise for us. You can tweak here a few more parameters, like making it in a probability terms, and you can download it as a CSV or JSON. That's a great point to actually remind that you can share the quantum program as a link with anyone. You can download it as a custom, as a LaTeX, and as a JPEG, JSON, transpiled custom. QProg is our own native format, and so on. Basically, you can get it as a custom or transpiled custom and then use it in Qiskit or something else. So you can still have the power of high level. And if you want also to take it to another platform or to load it to a specific computer which is offline and you don't have access from here, you still can use Classiq and get your custom file by us.
Another question.
Yes.
What's the default setting for depth and width? Yeah, if you don't have any preference.
Well, the default setting, I guess it depends on the algorithm, but well, if you do reset, you get no constraints at all. That's a good question. I think usually we go with depth, optimized with depth and no other constraints. So that's, well, the less constraints you have, the easier the problem is to solve. Yeah, so that's basically it. I guess it's depth.
Okay, thank you.
My pleasure. So I think we covered most of the functionalities of the platform. Yeah, I was just explaining about the exporting formats. So we can go back to the slides. Yes. So just wrapping up everything about the platform. So what is Classiq is basically software platform for designing, optimizing, and analyzing quantum algorithms, as well as executing them, while exploiting the power of high-level functional design. And again, well, yeah, you have the wrap-up video. And now let's discuss some further hands-on practice, and we can call it maybe continuous of the live demo. So this is our documentation page. I think the link was shared with you. You have here a link to the platform, to the community, and to the Classiq library, which I'm going to talk about now. Oh, yeah. So Classiq community is over 7,000 users where you can click here and communicate with us. We announce here about different events, workshops, many users give feedback for us here, ask questions for support on the platform or on quantum algorithms in general. So this is very much recommended. And if you're going to have further questions, that's the place to ask and stay connected with me. Rather than that, you have here all the things you need to get hands-on experience with the Classiq platform. So you can go to the user guide, to the library, the QMod reference to understand the syntax of the QMod native syntax, and also the SDK Python syntax, which I'm gonna talk about in more details soon. And the best way to start with Classiq is the Classiq tutorial. You can just click here in the documentation. Whoops, and I see I have a glitch. Well, I don't know what about that. well, we can access it to the Classiq library. Usually it's run very smoothly, but I guess we always have a glitch on live. So basically all the things you saw on the Classiq platform, here, all the algorithms you can access from here. You can access also from our Classiq library repository, where you can download the notebooks and run them on your local environment, or from the Classiq Studio. So you have the access to the Classiq Studio from our platform, and you're gonna get an remote Python environment where you can run all your algorithms. So that's here the Pythonic syntax, and you have these notebooks, as I mentioned, both in the documentation, in the Classiq library, and in the Classiq Studio. You can go, for example, tutorials, basic tutorials, and the Classiq tutorial. And over here, you can choose the best order is a Classiq overview tutorial, synthesis, and then the QMOD workshop. For example, you have it here. We can run it and see some more of the capabilities of the platform. This is basically covering the same flow we just did in the platform itself. And it's a very good way for you to get hands-on experience. So we already saw this example, right? Y equal x to the power of 2 plus 1. So we're just going to run it so we can get it on the platform. Let's restart the kernel. Right, I guess I need to refresh it. I opened it before. I just another note about the platform itself. We're gonna go back here after it's reloaded. I wanted to show you also the Bertrand-Vazirani example I showed in the slides. So here we have the exact same implementation we saw before. We have the Bertrand-Vazirani predict. We have the condition. We have the identity within the else statement. We have the within apply and the main function that aggregate everything. Again, we don't have here specific constraints rather than optimizing on depth. We can synthesize it. Waiting a couple of seconds while the optimized implementation is calculated for us. And we get an implementation with our interactive visualization. We can see the Hadamard. We can see the implementation of the function bview predict, and nicely presented all the information flow. And another example that I actually wanted to show you. So again, everything here is also available through the Classiq library. So I think the most interesting folder is the algorithms, where you have from Shor algorithm to the basic algorithm like Deutsche Joseph, Bertrand-Vazirani, the DQI, the new algorithm by Google, which is quite famous recently, the Grover, and so on, as well as quantum machine learning algorithms and quantum optimization algorithms. And this is what I actually wanted to run and show you. So the QAOA, the quantum approximated optimization algorithm, it's more advanced and complex algorithm, so don't get scared if you don't understand it all. But we have here some implementation, again, using the within apply. We have the cost, apply cost function for applying the cost layer, those of you who are familiar with the algorithm, and we have the apply all here for the mixer layer. And the reason I want to show you that because this is, let's say, somewhere between 20 to 30 lines of code, and you're going to get a very large implementation. I think it's quite impressive. And that's, again, demonstrate the power of the new paradigm and the abstraction of quantum software languages.
Another quick question.
Yes, please.
Is it possible to convert the COSM file into a Classiq code?
Oh, that's a great question. So the answer is, well, you can upload here, exactly here, as you see, both custom and a QProg formats. QProg is our own native format, which you can download from here. And you can upload a custom. But the thing is that if the code was created in a low level, so the visualization would be also in low level. So you will not have the abstraction. But let's say that you have implementation that you want to execute. So you can upload it and just press execute, and you have access to all the hardware providers. So the answer is yes, you can do that, but you're not going to enjoy our synthesis engine because you already have a concrete implementation, just as we saw in the presentation. The moment you have a concrete implementation, it could not be separated to higher level algorithmic concept and lower level implementation because it's already a rigid implementation. Great question. Thank you. So I just synthesized the QAOA knapsack example. We got 18 in width, 18 qubits, and we got above 2,000 gates in depth. So that's a very large algorithm. And you can see we have here the repeat probability. So we have few steps. We can see what each one of them do. It do the same. It's apply the cost layer and then the apply all. This is the mixer layer for those who are familiar with the algorithm. We can dive deep into a specific cost layer. We can see the arithmetic expression. We can see the control. We can see it uses a Suzuki trotter. We can see how it uses the Suzuki trotter with control RZ rotations. We can go back to higher level and check this building block again with a lot of arithmetics. We can zoom out, and that's basically it. Again, very, very convenient way of looking on the algorithm, both on low level and high level at the same time. And just to scare you how it would look like if I do expand all. So this is what we show in one of the slides, why it's basically useless because you cannot see the information flow from this view of the entire 2,000 layers of gates. That's just a mess. And I think that's demonstrate again pretty well why we prefer it in building blocks where we can see everything from above, but also deep dive into a specific layer. So again, all of these algorithms are available also in our Classiq library. We have many contributors that implement papers and different algorithms and functions, tutorials, and applications. If you are interested, after you get some hands-on experience to contribute, you are welcome. Just read the contribution guidelines and open an issue and discuss with us before you implement it. Let's see, I hope this crash is now fixed after refreshing. Let's restart the kernel again. So we import everything. We run it. Let's see. Well, I have an authentication problem. Well, I promise you guys that usually it works perfectly. It's relatively new feature, but basically you can run it also on your local environments. But I do encourage you to try it on our environment because that's probably some, you know what? Of course, it worked before the workshop. Anyway, that's a pre-installed Python environment for you, which usually works. And if not, it probably will fix ASAP. But here in the Python version, you have all the power of the domain-specific mode with the power of Python. So quantum machine learning applications and all the all the hybrid algorithms so could be implemented from there. Again, the library, I see there is just a glitch. It's probably because of the new version released today. I'm sorry for that. Let's see if I have some workarounds. I guess GitHub is reliable.
Related to this question,
Yes, please.
is there support for version control or collaborative coding with the Classiq environment?
If there is, again,
If there is a support for version control,
what do you mean by that? We have support. Generally, we're supporting all user and answer all questions within our Slack community. So supporting questions, me and my team are over there. We answer questions. If you refer to how many version backward are compatible, so yeah, it is backward compatible to a certain degree. You can find the details within our documentation page. So in getting started and installation, registration and installation. So everything is explained here, including what Python versions you need on your environment and how many versions we support backward. As we move on, we try to be more and more stable. We already did a long way and the product is very much stable. We had a version released today, so this is why it's a little bit glitchy. Usually it's much more smooth, and I hope now I can run it through here. Actually, I can also show you my local Python environment over there. It runs smoothly, but I actually wanted to show you, yes, this one. So I think, yeah, so there is some authentication problem. Usually it's very much smooth. So that's it. If you have further questions, Dimitri, that's a great time. I can quickly check my local environment to show also the Pythonic syntax. Mm, mm, mm. Yes, so I didn't plan to do that, but we can do that. So is my Jupyter Lab is visible? Yes, I guess it is. So this is just a random notebook, but basically here you have the Classiq library. We can go tutorials. We can go basic tutorials and the Classiq tutorial. And the best way to practice further is Classiq overview. Then, whoops. Classiq overview, synthesis tutorial, and then the QMod workshops. So the Classiq tutorial. So I just ran everything. You can basically see again, it's the same example we already showed. And all the details of the flow from modeling, synthesizing with optimization and execution. And you saw I executed the algorithm, or I synthesized it and pressed show, and I get here X in Hadamard transform, and then I get Y, which is it coherently calculates X to the power of 2 plus 1. I can execute it on our simulator. And I get already interpreted, you see here, so X equal 0 give us Y equal 1, X equal 1 give us Y equal 2, and so on. So Y equal 5 when X equal 2. And you see, you already get it interpreted, and not as a bit string, which is very convenient because different hardware providers usually bring you just bit strings from right to left and left to right, which could be less convenient. Again, you can change it to probability if you prefer, and not to counts, and then you get it this way. You can close it and go back here. So this was synthesize and show right after I created the quantum model from the main function. And yeah, you can execute the quantum program also directly from the Python notebook. You don't have to go to the platform itself. So you can execute it, and then you can print the parsed results. So you can see x equal 5. You can plot it with matplotlib and use whatever you want to do in Python. So I very much recommend going through this Classiq overview to hands-on experience the tool we suggest and the high-level way of thinking. You have here a summary, food for thoughts, and some further practice. In the synthesized tutorial, you can play further with this example, setting some constraints, optimizing for depth. I will not go into much details here now, but you can then create the same program with width optimization, and you can see the different circuit you're going to get for different constraints. And if you want to go to the QMod tutorial later on, so we have two parts of it. This is if you really want to dive deep into the platform and get really experience with the best tools available nowadays in quantum software. So we have here many explanations and a lot of exercises. So we demonstrate the concepts here nicely and in structured manner, and you have the solutions for those exercises here in the end. So that's it. Again, if you have any question, you are welcome to communicate with us in our Slack community. Supporting questions, general channel with many announcements, feedback, we take it into account. We communicate with our users and always there to support. That's it. I think that's it. I very much recommend rechecking it tomorrow, the Classiq Studio, because that's a pre-installed environment with no need to authentication. Today it's a glitchy day, I guess, but it is a new feature which are getting more and more stable. And let's see if I covered everything. All right, yes, I only missed one point, advanced algorithms and tutorial, where I partly covered it. So as I mentioned, we have the algorithms folder with a bunch of algorithms and the tutorials, where we have the basic tutorials, but we also have different tutorials like advanced tutorials, discrete quantum walk, high-level modeling of flexible quantum phase estimation, and so on. So very much recommended to get hands-on. And we are here to support you with any question in the Slack community. So please stay connected. And thank you very much. I hope you got some value and learned something about the change of paradigm in quantum software. And I hope to get engaged with you in the Slack community. Thank you, everyone. Thank you, Dimitri, and thank you to the AI for Good Summit and the Quantum Coalition for organizing this session. And thank you for listening.
Yeah, thank you so much for your talk. We have a few minutes left, so I'll probably ask a few questions.
Go ahead.
So they will be a little bit less technical. The first one is, what role can academic or open source communities play in tackling the software challenges?
Again, please.
What role does the community play in Classiq ecosystem? What part of Classiq is open source, and yeah, what role can?
All right, that's a great question.
Yeah.
So as I mentioned, currently, there is a need in academic license, in academic email to use the platform for free. Basically, academic use is completely for free. If you do pursue research, so you can use Classiq and to implement your algorithms with it, get our support, and that's completely for free. If it's a commercial use, so it is our sales department get involved, and there is a need for a license. Basically, the repository is under MIT license. I'm not a code licensing expert, but this algorithm library is completely open source and for free for academic use and for educational purposes. I hope it's answered the question. And yeah, we do have, as I showed, many implementation currently ongoing from users. We communicate with them, we give them feedback, and we integrate within our algorithms library a good implementation that meet our standards. What I can add about that, yeah, what's special about the Classiq library? This is the largest collection of quantum algorithms that are maintained. Why it's so important? There was the question before about maintaining, supporting older versions. So let's say, Dimitri, that today you contribute your algorithm into our Classiq library, and tomorrow we change the syntax, we change something within our language, we change the way we implement some stuff. If it's contributed to the Classiq library, the code remain maintained. We maintain all the code within the Classiq library. So basically, the algorithm will be valid for the future. And we see the Classiq library as the future gateway to implementing quantum algorithms. And this is very much with collaboration with the community. So that's just maybe this is the best way to visualize it. Just one example. For a notebook, which is currently in a review. So one of our users implemented a paper solving differential equations with a quantum algorithm. So including markdown, math description, feedback from me in this case. And that's a very nice implementation of the algorithm, code blocks, and so on. So we take it seriously, and we invest a lot of efforts in maintaining all of these algorithms. Yes, please, if you have further questions.
Yeah, thank you. And also, in your opinion, what is the biggest advantage of Classiq SDK
Well,
or Classiq platform in general?
I guess it's hard to answer because I do believe in a couple of very strong points in the product. First of all is the language itself, which kind of abstracting quantum concepts to high level. And of course, the optimization engine that basically let you use the same code and tweak one parameter or add few constraints and get completely different implementation. In the past, I worked in a research project with Qiskit when I was in Munich, and I implemented an algorithm and I tried to run it in simulator and everything was great. The moment I wanted to run it on real hardware, I had to tweak so many different parts of the code. So in Classiq, we, from the beginning, thinking about the flexibility of the algorithm to be suitable for every hardware, gate-based hardware modality. So I think the flexibility of the product is great. And as I showed the visualization tool, I think this is one of its kind. The interactive way, the ability to see, to know that the bunch of gates over here are obeying this arithmetic expression, that's really unique rather than just watching a bunch of gates, which might be confusing. And of course, the integration with all hardware providers. So it's kind of the fact that it's a end-to-end platform. And
Okay.
again, we are very much, if there is in the crowd researchers or students, we're really happy to support research projects. So our algorithms team is very much involved in different research projects. And please let us know if you have cool implementations. We can support you. We can upload them to the library and so on.
Yeah, that sounds great. And I think lastly, you mentioned how you participated in IQUAC 2024, and to this end, there's a question: what advice would you give to the Flick participants?
Click participants. Well, honestly, come to learn and enjoy. Even if you're not gonna secure the first place, you're gonna get hands-on with the most modern tools in quantum software. But rather than that, read carefully the instructions, understand how you're gonna get scored, understand the problem, understand the tool, get prepared. So if you want to participate in the hackathon, you're gonna have 36 hours to create a quantum program to solve a problem. It's enough time to solve a problem, but usually it's not enough time to solve a problem and to learn a tool from scratch. It is possible to do them both in 36 hours, but that's requires some talent and luck, I guess. So going through these Classiq overview to understand the flow of the quantum modeling with Classiq, go on through the synthesize tutorial, go with the QMod workshops afterwards to get a hands-on experience with that. And later on, you can, I don't know, go with your curiosity, read about Hamiltonian simulation or quantum machine learning, optimization. This is already more open, or just go through algorithm that you find interesting, see how it's implemented, and get familiar with more and more parts of the product. I guess that's the best advice I can give you for the hackathon. Get familiar with the tool, come to learn, and come to enjoy.
Hey, thank you, Nadav. The great workshop. Yeah, we are all looking forward to the hackathon itself.
Yes, me as well. Thank you, Dimitri. And again, I encourage everyone to participate, to practice before the hackathon and ask questions in the community. We will be there to support you to get prepared for the hackathon.
Hey, thank you. Goodbye, everyone.
Goodbye. Thank you.